A free particle on a circle. A particle is confined to move on a circle with radius capital R but is otherwise free. We can parameterize points on this circle by using the distance x from a reference point or by using the angle theta equals x divided by capital R. Since x equals to 0 and x equals to 2 pi capital R describe the same point, the wave function must satisfy psi of x is equal to psi of x plus 2 pi r and the derivatives also. Part A, solve the free particle time-independent Schrödinger equation subject to these boundary conditions. You should find solutions psi sub n plus or minus, where n is a positive integer and where lower n corresponds to lower energy. Express your solutions in terms of theta using unspecified normalization constants a sub n plus and minus correspondingly, respectively, to modes that move counterclockwise toward higher x and clockwise toward lower x. Part B, normalize these functions to determine a sub n plus and minus, and part C, what are the energy levels E sub n. So we're going to start with writing time-independent Schrödinger's equation for a free particle, noting that the potential energy is 0. The time-independent Schrödinger's equation is minus h bar squared divided by 2m, second derivative of the wave function d squared psi dx squared is equal to energy times psi. And here we're parameterizing it so that x is equal to capital R theta and dx is equal to capital R d theta. All right, now if we write the first derivative of the wave function with respect to theta, d psi d theta, this is equal to the derivative with respect to x and the derivative of x with respect to theta. So derivative of x with respect to theta, you can see here, is capital R. So this is capital R times d psi dx. If I go to the second derivative, d squared psi d theta squared, now I have to take a derivative with respect to x of d psi d theta and then multiply it by dx d theta. And d psi d theta is capital R d psi dx, so its derivative with respect to x is capital R times the second derivative with respect to x, but dx d theta will give me another capital R, so this is capital R squared d squared psi dx squared, as we can see here. Okay, so we realize that from this result, d squared psi dx squared is 1 over r squared times d squared psi d theta squared. So that's what I will substitute here. So d squared psi dx squared is 1 over capital R squared d squared psi d theta squared, and substituting that into Schrödinger's equation, I have minus h bar squared over 2m minus h bar squared over 2m multiplied with 1 over r squared d squared psi d theta squared is equal to energy times psi as a function of theta. Now I have written this in terms of theta, or I can isolate d squared psi d theta squared, and now I will have this term 2me r squared over h bar squared with a minus sign here, so to the left it will come with a plus sign. So plus 2m capital R squared divided by h bar squared energy times psi. This is equal to 0. So let me move this a little bit to the left. This is equal to 0. Okay, so we can write the characteristic equation for this differential equation. Characteristic equation is L squared plus 2m capital R squared E divided by h bar squared is equal to 0, which has solutions. L is equal to plus or minus I capital R divided by h bar square root 2m E. And let's call this plus or minus I n. So the solutions are of the form psi of theta is in the form a plus e to the in theta plus a minus e to the minus in theta, we can see. Now, for counterclockwise motion, I'm going to use the plus as suggested. So psi sub n plus of theta is equal to a plus e to the I n theta. And I have to satisfy this boundary condition as well. So the other thing I will need is its derivative, psi n plus prime of theta. That will be I n a plus e to the I n theta, the derivative with respect to theta. So let's check the boundary conditions here. Psi of theta plus 2 pi, which means x goes from x to x plus 2 pi r, is equal to a plus e to the I n theta plus 2 pi, which means this is a plus normalization constant e to the I n theta e to the I 2 pi n, that is equal to the wave function itself if n is an integer. So that I have cosine 2 pi n, which is 1, plus I sine 2 pi n, which is 0. So this is going to give me 1 here, which will give me the same wave function. If I look at the derivative, psi prime of theta plus 2 pi, that is a plus in e to the in theta plus 2 pi. This will be equal to in a plus e to the in theta e to the I 2 pi n, which is the derivative of psi n plus at angle theta. So these conditions are satisfied if n is an integer. So I could do the same thing similarly for the minus solution, and similarly for psi n, psi sub n minus. So I can write the solutions as psi n plus is a plus e to the in theta, and the minus solution, psi n minus, is the normalization constant a minus e to the minus in theta, where n must be an integer. These are the solutions to the time-independent Schrödinger's equation satisfying the given boundary conditions. Now in part B we were supposed to find the normalization constant. That's the condition of existence. The particle must exist between x equals to 0 and x equals to 2 pi capital R on this circle. So if I look at the normalization condition, integral from 0 to 2 pi R, psi complex conjugate psi dx is equal to 1, which is absolute square. So this is going to give me integral from 0 to 2 pi R a plus square. The complex conjugate will give me minus in. Theta is x over r. Minus in x over r. The wave function itself has e to the in theta, e to the in x over r dx. This is equal to 1. So since this product gives me just 1 here, I will have a plus absolute square multiplied with x. The integral will give me a plus square dx. Evaluated between 0 and 2 pi r, it gives me x goes from 0 to 2 pi r, so it's 2 pi r is equal to 1. So I can evaluate the normalization constant a plus as 1 over square root 2 pi r. This is a plus. And if x goes to minus x, I have the integral from 0 to minus 2 pi r in the clockwise direction. That is a minus square e to the in x over capital R, e to the minus in x over capital R. That's x over capital R is theta. And here I have minus dx is equal to 1. So I will obtain, because the angle is going negative here, a minus absolute square multiplied with minus 2 pi r gives me 1, so that my a minus is the same thing, 1 over square root 2 pi capital R. Okay, so that's the minus solution, that's the plus solution. They have the same normalization constant. Now I'm supposed to find the energy levels corresponding to this. So let's substitute the solution psi sub n plus into Schrödinger's equation. So second derivative of psi with respect to x is equal to, because we have e to the in theta here, e to the in x over r, it will give us a factor of 1 over r, the second derivative 1 over r square, in so from the second derivative we will get in twice, in square, and then we will have a plus e to the in theta, which is x over r. Now this will give me minus n square over capital R square psi n plus. So when I substitute into Schrödinger's equation, minus h bar square over 2m d square psi dx square, which is minus n square over capital R square multiplied with psi n plus is equal to energy times psi n plus. So I calculate the energy levels because the minus signs disappear here. The wave functions will disappear from both sides. I obtain the energy levels. The energy levels are n square h bar square divided by 2m capital R square. Now if I were to use psi n minus, instead of I n square here, I would get minus I n parenthesis square. And since I have parenthesis I n square equal to minus I n parenthesis square, the answer will be the same. The answer is the same for psi n, psi sub n minus. These are the energy levels corresponding to these two solutions. Okay, so we have a free particle confined to move on a circle with radius capital R. First, we were asked to parameterize points on the circle by using distance x from a reference point on the circle, and the angle theta is x divided by capital R. Since we have periodicity with capital R or in angle 2 pi, the wave function must be the same at the beginning and at the end point because those 2 points are the same, and the derivatives must be the same. So first we solved time-independent Schrödinger's equation with this parameterization, and we realized that the second derivative with respect to theta of the wave function is related to the x derivative with r squared times d squared psi dx squared. So for this one, we substitute 1 over r squared d squared psi d theta squared, and we obtain the differential equation with the characteristic equation given here, which suggests we have two types of solutions, a plus e to the I n theta and a minus e to the minus I n theta. So I call this capital R over h bar squared 2me n. So for counterclockwise motion, if we substitute theta and then theta plus 2 pi, where we have to have periodicity, we obtain the same wave function if n is an integer. So we find that n must be an integer. Also, the first derivative gives us the same condition. And if we do the same exercise for the minus solution, we get the same result. So we obtain the wave functions a plus e to the I n theta and a minus e to the minus I n theta with n an integer as solutions to time-independent Schrödinger's equation. The particle must exist between the beginning point and the end point. X equals 0, x equals 2 pi r, or theta equals 0, theta is equal to 2 pi between these 2 points. So we write the normalization condition, the integral between the two endpoints, absolute psi square, which is psi complex conjugate times psi dx is equal to 1. So complex conjugate of this gives us e to the minus I n theta. Complex conjugate of this gives us e to the plus I n theta. So if we perform this integration from integral 0 to 2 pi r, x goes from 0 to 2 pi r, the psi complex conjugate psi dx, we obtain a plus must be 1 over square root 2 pi r. It's a real number. If we do the x to minus x transformation, so that we have we're going from 0 to minus 2 pi r, or we could say we're going from minus 2 pi r to 0 because it's for a clockwise rotation. So maybe that's better to express it that way. So we're going from minus 2 pi r to 0 with clockwise rotation with plus dx. And that would give us a minus is equal to 1 over square 2 pi r also. Remember, a plus was for clockwise rotation, a minus was for counterclockwise rotation. So we go from minus 2 pi r to 0. So if we substitute these solutions into Schrödinger's equation, we obtain the energy levels. Also, if you go back here, we had N is defined as R over H bar squared 2 me, so we already know the energy levels here. But if you do it explicitly by substituting the solutions, we also recover the energy levels given as N square H bar squared divided by 2m capital R square. And because in the second derivatives you obtain in parenthesis square or minus in parenthesis square, the answers are identical for the two different types of wave function solutions.